Let us demystify how a 64-square chessboard can have more game variations than there are atoms in the universe together, really quickly. It sounds absolutely bonkers, right? A simple wooden board with 32 pieces, and yet the sheer number of possible games played on it could dwarf the entire observable universe's atom count. When I first heard this, my brain also hurt. It feels like a paradox, something that defies common sense. The secret behind this seemingly impossible claim is simpler than you think, although it involves numbers so large they are hard to grasp. This is not just a quirky fact, it is a powerful illustration of how quickly possibilities can multiply, even from incredibly humble beginnings. We are talking about exponential growth on a scale that makes your head spin. It starts with the simplest of choices. Imagine a chessboard, a familiar 8x8 grid of 64 squares. At the beginning of a game, you have 16 pieces for each player, arranged in their precise starting positions. Every game begins from this identical setup, but from there, the paths diverge almost immediately into an explosion of possibilities. First, consider the very first move. White has 20 possible opening moves. Each of the 8 pawns can move 1 or 2 squares, and each of the 2 knights can move in 2 different L patterns. That is already a significant number of starting options before Black even gets to play. Then something interesting happens. After White makes their first move, Black also has 20 possible replies. So, after just one move by each player, how many unique sequences of moves have occurred? It is not 20 plus 20, but 20 multiplied by 20, which gives us 400 different possible game states after just 2 half moves. Building on that, the number of choices only grows. Each subsequent move opens up even more possibilities because more pieces are active, and the board state changes drastically. Pawns can capture, knights jump to new squares, bishops and rooks gain open lines. The complexity compounds with every single turn. What is fascinating is how quickly these numbers become astronomical. After 3 moves by each side, there are over 9 million possible positions. And this is just 4 moves into an average game. This is not just about winning or losing, it is about the sheer combinatorial power of a seemingly simple system. This leads to Shannon's number, named after Claude Shannon, often called the father of information theory. He estimated the lower bound of the geometry complexity of chess to be around 10 to the power of 120. Yes, that is a 1 followed by 120 zeros. To put that in perspective, the number of atoms in the observable universe is estimated to be around 10 to the power of 80. So, 10 to the 120th power is an unfathomably larger number than 10 to the 80th power. It is not just a little bit bigger, it is a difference of 10 to the 40th power, or 10,000 billion times larger. The key is understanding the difference between linear and exponential growth. If you add possibilities, the number grows steadily. But when you multiply possibilities at each step, the numbers explode. Each move in chess is not just adding an option, it is creating a whole new universe of subsequent options. Imagine a simple maze. If it has one path that branches once, that is 2 options. If each of those branches again, you quickly get 4, then 8, then 16 paths. A chessboard is like a maze that constantly reconfigures and branches thousands of ways at every single turn. What happens next is crucial. This is not just about good moves or optimal games. Shannon's number includes all theoretically possible move sequences, even terrible ones, or games that end quickly. It is a measure of the total potential states and paths, not just the ones a grandmaster might consider. Ultimately, it is about decision points. Every time a player makes a move, they are not just choosing one square, they are choosing a path through an incredibly complex decision tree. Each choice eliminates billions of other paths while simultaneously opening up new ones for their opponent. Let us begin with thinking about the game state. A game state is simply the position of all the pieces on the board at any given moment. From that state, how many new states can you reach in one move? That is what drives this incredible complexity. As we move forward, consider the average length of a chess game. It is often around 40 moves per player, or 80 half moves. So, You are not just multiplying 20 by 20 a few times, you are doing it potentially 80 times over, each time with an even larger set of options available. Here is where it all comes together. Each branch of the game tree represents a unique game. The sheer number of these branches, even if many lead to dead ends or checkmates quickly, is what accumulates to this mind-boggling figure. It is a universe of possibilities contained within a tiny wooden box. The foundation is the simple rules of chess. These rules, though few, allow for an unimaginable number of interactions between the pieces. Each piece has its movement pattern, and combined, they create a dynamic system of attack, defense, and strategic positioning. Building on that, the freedom of movement within the 64 squares means that positions are rarely identical. Even if two games look similar, a subtle difference in one pawn square can lead to entirely different outcomes, cascading through the game. Where this takes us is an appreciation for combinatorial explosion. This is not unique to chess. It is a principle seen in many complex systems, from molecular biology to computer science. Small changes or decisions at each step can lead to wildly different final states. Consider how human intuition and strategy work within this vastness. We do not consider all 10 to the 100th options. Grandmasters, or even advanced AI like AlphaZero, prune this tree, ignoring impossible or clearly bad moves to focus on the most promising paths. Looking closer, even with pruning, the number of reasonable moves at any given point in a chess game is still quite large, typically in the range of 340. So, the multiplying factor for possibilities remains very high throughout the game. Developing this idea, the real insight is that a system does not need to be infinitely complex to generate an effectively infinite number of outcomes. It just needs enough decision points and enough options at each point for the numbers to snowball beyond our comprehension. What becomes clear is that the simple act of moving pieces on a board creates a universe far grander than the physical universe it exists within, at least in terms of potential sequences. This is a profound testament to the power of mathematics. To understand this, think about the unique identity of each game. Even if two games have the same winner and loser, the specific sequence of moves that led there makes them distinct. Shannon's number accounts for every single one of those distinct paths. Progressing from there, this concept helps us appreciate why computers struggled with chess for so long. They had to evaluate a huge portion of this game tree. It took massive computational power and sophisticated algorithms to even begin to navigate this labyrinth of choices effectively. The conclusion? The number of atoms in the universe is a static, albeit enormous, quantity. The number of possible chess games, however, is a product of combinatorial logic, a dynamic and explosive force that grows exponentially with each decision. The most important part is that this is not just a fun fact. It is a demonstration of how systems with simple rules can generate incredible, almost infinite complexity. It is a reminder of the power of emergent properties in nature and mathematics. Ultimately, the point is that while our human brains cannot possibly visualize a number like 10 to the power of 120, we can understand the process by which it arises. Repeated choices, each multiplying the available options, turn something small into something truly cosmic. The essence of it all comes down to the fundamental difference between counting distinct, static objects, atoms, and counting unique, evolving sequences of events. Chess games. One is a measure of quantity. The other is a measure of potential paths. So the big picture? A 64-square chessboard is a miniature universe of strategy, logic, and infinite possibilities. It is a profound example of how seemingly simple rules can create an almost unimaginable depth of complexity, far exceeding the physical limits of our observable cosmos.